Okay, guys, welcome. Today we're going to talk about the Diffie-Hellman Key Exchange. Okay, so we're going to put together all the ideas that we discussed so far in sort of this cryptography aspect, and we'll use that to explain the Diffie-Hellman Key Exchange. So the idea behind this is to look at Z mod P, where P is a large prime number. And of course, by large, we could mean thousands of digits. Okay, so what we're going to do is we're going to suppose that Matt and Trey want to exchange messages using a traditional system, we'll just say called two-fish, which requires a key positive K, or positive K, capital K. But the problem is that they're physically far from each other, and they don't have access to any secure channels of communication to exchange a common key. Now, they do, however, have an insecure communications available, right? And this could be something like email or Facebook or Instagram or even postal mail or something like that. Now, Seth and anyone else who wants to can listen in on any of this insecure communication in some way, right? So Seth is sort of the enemy in this idea, and Matt and Trey are going to communicate on this insecure communication channel, right? Which Seth could potentially view if he wanted to. Okay. And like I said, the insecure channel could be something like email or Instagram or postal mail, something like that, right? Something that is in some way breachable in terms of its security. Now, if Matt picks a capital K that he wants to use, he can't send it to Trey because Seth is monitoring their communications, and he would find out what K was, and then he could decrypt all of Matt and Trey's messages, right? Which would not be good. Now, Matt and Trey come up with a solution in a long email thread, which ironically enough says Seth will read as the idea materialize. But the interesting thing is that this doesn't help Seth at all right, which is sort of interesting here. So here's the process. We have that Matt and Trey pick a very large prime number P, right? Now they also pick G such that for every, they pick a G such that for every A, the GCD of A and P is 1, implies that there exists a K such that G to the K is congruent to A mod P, right? So a lot of sort of things going on here, but what's essentially happening is that we're picking a G such that for any prime, for the prime that they chose and any other number that are relatively prime, there exists some K such that G to the K is congruent to A mod P, right? And of course, this is also known as a primitive root mod P. Now they choose this as a base for an exponential function, right? So they choose this G value. Now both the values G and P are public, right? Or of course non-secret. And of course Seth can see them if they're public. Now for convenience, let's just suppose that Matt and Trey chose their prime to be 23 and their G to be 6, right? And of course this data is public. All right, now in practice, they wouldn't use these small numbers because in practice, you would want to use large numbers, so it's even harder to decrypt. Okay, now Matt chooses and we'll put it in quotes here, large random value, because in here, our large random value isn't really that large, but this value is 4, and we're going to call this M sub 0. Now this is private. He hasn't shared this with anybody. He's just chosen this for now. Now Trey also does the same thing, chooses a large random value, and his value happens to be 8 in this example. And of course, this is private. Now, what's the common secret key that they establish? Well, Matt is going to find capital M, which is G to the M sub 0 mod P, which in this case is 6 to the 4. And if you were to compute that, would give you a 1296. And when you divide that by 23, you would find that your M is congruent to 8 mod 23. And then Trey does something similar. He takes G and instead raises it to the S sub 0, right, which is the number that he found. So this is 6 to the 8, right? So then we get this 1,679,616, which once you divide it by 23 will give you a remainder of 18. Okay. Now 8 and 18 would then be exchanged on the insecure channel, and we now consider them public, right? Because they were transferred along the insecure channel. Now Seth sees 8 and 18, but he can't find what M sub 0 and S0 are from them, since Seth would need to solve these two equations, right? We would need to solve 6 to the x power is equal to 8 mod 23, and 6 to the x is equal to 18 mod 23. Now, in this, you might be able to find out what it is if you were to sit down and test values of x for long enough, right? And of course, that would be the only way to do this. But you can imagine that if p was extremely large, this would be essentially impossible to do. Okay. Now, upon receiving this value s, Matt then computes s to the m sub 0, right? And when he does that, that's 18 to the 4th, which is 104,976, which mod 23 will be congruent to 4, right? And then Trey does something similar. He takes his m to the s sub 0, and that's 8 to the 8th, which is this large number here, which once you divide it by 23 would give a remainder of 4. So since these both come out to be the same thing, that's the secret key, right? That's k equals 4, and of course that's private. Now the reason why these are equal is because of your exponent rules, right? This is g to the s0 to the m0, which of course is g to the s0 m0. And then the other one is just the reverse order, but multiplication of integers, of course, is commutative, so we get the same thing. Okay, and of course, the whole reason why Seth can't figure this out is because he cannot compute M0 and S0, right? And that's what holds this whole thing together, right? Now, in DHM, right, this Diffie-Hellman exchange here, and virtually all other public key systems, there's a danger that, of course, Seth would figure out a clever way to find K from the public data, right? And of course, the whole idea, the whole science of cryptography is a group of mathematicians and computer scientists are trying to prove the fact that Seth cannot do this, or trying to prove ways that Seth could do this, right? So that concludes this video on the Diffie-Hellman exchange, the key exchange. I hope you enjoyed, and I will see you next time.